Thank you, everyone, for attending today's Foxconn Quantum Computing Seminar. Today, we have the pleasure of having Marcel Hinsche to give us a talk on single copy stabilizer testing. So Marcel is a PhD student with Jens Eisert in Freie Universität Berlin. He is fifth year and looking for potential postdoc opportunities. He's interested in things related to Clifford's and the stabilizer formalism across quantum information, and has worked specifically on applications of these things in the realm of quantum learning and quantum property testing. So Marcel, the floor is yours.
Thank you very much for the introduction. Yeah, and thanks for inviting me to your seminar. So let's jump right in. No, wait. Yep, okay. Can you see my cursor?
Yes, the mouse pointer, okay. Right?
Very good. So yeah, before starting, I want to give a shout out to my co-author, Jonas. Jonas is a PI in Amsterdam at CWI, and he's a super nice person. If you haven't met him so far, I really recommend you get in touch at some point. I really enjoyed working with him. So in this paper on single copy stabilizer testing hit the archive on October 10th last year, so it's still pretty recent, and I haven't given this talk to anyone else yet, so you're basically also having to indulge me for the first time. Yeah, let's see how it goes. So my plan for the talk is basically to, for the first part, just to deconstruct the title and explain what the words mean, and hopefully by the end of the talk, at least everyone can walk away and understand what the title actually means. So let me do that. Let me start with the second part of the title. So stabilizer testing, what is that? So as you might think already, it has to do with stabilizer states. And stabilizer states are like this vast class of quantum states that have efficient classical representations. And because of this, they're very useful in all different kinds of areas in quantum information. In particular, they are very crucial for quantum error correction, at least mainstream quantum stabilizer codes. But they're also interesting in classical simulation, like Jakob knows this. He has worked on some stuffs in this regard. And also in quantum communication, where we build quantum networks maybe based on graph states, which are a particular subclass of stabilizer states. So in summary, they're basically all over quantum info. And what are they mathematically? Well, they're just +1 eigenstates of stabilizer groups. And stabilizer groups are subgroups of the Pauli group, where all the Pauli operators in the subgroup commute. So stabilizer states, basically, they satisfy this equation here for some Pauli operators belonging to some group of commuting Pauli operators. Okay, and for the purpose of this talk, just to clarify it already in advance, whenever I say stabilizer state, I mean a pure stabilizer state. So the corresponding stabilizer group is maximal in the sense that it has, for an n-qubit state, it has n generators. Okay, but this is not really important just yet. For now, it's really important that we all agree that stabilizer states are an important class of states that's interesting to study. But there's one thing that stabilizer states lack, and that thing is magic. It's a very fancy term. But really what it means is just magic is a resource that quantifies a non-stabilizerness of some state. And why do we care about this resource? Well, because it's well known that if we have stabilizer operations, we can supplement them with this resource of magic, maybe in the form of magic states, for instance. And that is sufficient to yield universal quantum computation. So this is the reason why people have, for quite some time now, wanted to study this resource of magic. and understand how to quantify the magic in some states. And one way to quantify this resource of magic is through a geometric approach, where we can just look at the set of all n-qubit stabilizer states and quantify or like define the magic of some other state, psi, some arbitrary state, as the distance to the set of stabilizer states, where distance here is measured with respect to fidelity. And for now, I'm just focusing on pure states here because that's easiest, and for simplicity, it's really all that I want to do in the talk. So again, magic for me just means how far is it from the set of stabilizer states. And if you know your stabilizer states a little bit, then you know that this picture is horribly sort of disproportionate to the reality of how the set of stabilizer states actually looks. It's actually just a point set that is where every point is quite separated in state space, but that's much harder to draw. So I decided to make this caricature here this way. Okay, so with this in place, I can already define what stabilizer testing is. It's a very simple task. The input to the task is just copies of some unknown state psi. And your goal is to decide if this unknown state is either a stabilizer state or it is at least some epsilon distance away from the set of all stabilizer states. So in this picture down here, there are basically two possibilities. You're promised that your unknown state psi either lives here in the set of stabilizer states or in the outer shell here. So it's at least some non-trivial distance away and has thus some non-trivial amount of magic. And this epsilon really is just there to assure that you don't have to go to infinite precision to distinguish these two cases. So it's like a standard promise gap definition of a task. Okay, so now the task is easy to state, but because maybe, I don't know how many of you have worked in quantum learning or quantum testing problems before, I just want to make some comments on how you should think about this task and how you should think about solving tasks of this kind. So basically, the model that we have in mind is you get given copies of the unknown state psi, and then you can apply a quantum learning algorithm to these copies. And what this algorithm is going to do, it's going to do some or apply some measurements on the copies of psi and collect some classical data this way. Basically, you're extracting information about the state psi copy by copy. And then you can classically process this data in whatever way you want in order to come up with some prediction about whether the state psi is a stabilizer state or not. That's how you should think about how these problems and algorithms for these problems work. And what we're usually interested in these kinds of problems is to characterize the complexity of such problems in terms of two standard metrics. One is time complexity. So how complex is the algorithm in terms of like maybe depth of the circuits that you want to apply, but also how complex is the classical post-processing, how much time does it take? And sample complexity refers to the number of copies in this picture here, T, that you need to make a good prediction. So in my case, because we're just basically having to decide a yes/no question, the goodness of the prediction is basically how sure can you be that your yes/no answer is going to be correct, or what is the probability of success? Okay, and if most of you might already see that this setup here is the standard setup of quantum property testing or quantum learning theory. So all sorts of questions can be phrased in this model. For instance, quantum state tomography is also an example, or quantum shadow tomography are also questions of this type that have the similar setup where you get copies of the state, you have a quantum learning algorithm, and you're supposed to make predictions based on data that you obtain by extracting information from the states. Okay, so stabilizer testing is really the marriage of two things. It's the marriage of quantum property testing applied to this resource theory of magic. And what we're trying to test for is, is the state magical or not? Okay, if there are any questions so far, I guess now is a good time to jump in. I have a sip of water.
There's something I just wanted to ask. So, okay, I guess one possible algorithm would be if you allow me to have a projection onto the stabilizer subspace, and then I can just sort of apply this kind of measurement to a copy and see if it goes through or not. But I suppose of course there's a question of how realistic would be this kind of algorithm to implement, I suppose.
Right. Yes, this is actually exactly the thing that I'm going to come to now, but your intuition is exactly correct. And the best known algorithm for stabilizer testing without any restrictions does exactly what you just said. It's sort of a measurement. It's a measurement that accepts all stabilizer states and basically rejects every other state. Right. Okay. But this nicely brings me to the next part of explaining the title. So hopefully the stabilizer testing has a check mark now, but now we can look at the single copy part. So what does single copy mean? In recent years in quantum learning theory, there has been this trend of sort of scrutinizing the algorithms that we have developed so far, again, and trying to understand how realistic they are, in exactly the way that the question was just addressing. So are the algorithms that we have developed so far actually experimentally feasible? And while you should really evaluate this on a case-by-case basis, we can sort of group algorithms in broad categories by just looking at some very broad features of them. And one of these features is a distinction between what I call single versus multi-copy algorithms, but some other people have different terminologies. For instance, I've also heard the terms incoherent measurements and coherent measurements, or entangling measurements and non-entangling measurements. So be aware that there are some different terminologies out there for the concept that I'm now explaining. Basically, a single copy algorithm, the way that it processes inside the algorithm is as follows. Basically, you get a fresh copy of your state, and immediately you're going to make some measurement M1 on it, and you're getting some outcome. And then you do the same thing again. You get a new copy, you make a measurement on it, get an outcome, and so forth. And then maybe in each of these errors here, I'm hiding some processing that you could be doing on the outcomes obtained so far. But the key thing is that single copy algorithms, they always apply the measurements to just one copy. On the other hand, something more general that you could do is you could apply a measurement across two copies of the state at once. So this is why people sometimes might call it an entangling measurement, because now here, if you think about this as a unitary and then measuring in some basis, for instance, that unitary would have to be entangling across the two copies of rho. So this is already a multi-copy measurement, but it's just a two-copy measurement, I would call it. The most general thing that you could do is really take all your copies that you have available as an input to the problem and apply some gigantic measurement across all of them, then just get a single outcome and do some processing. Okay, so this distinction is useful in the sense that generally we think of the algorithms on the left here, the single copy ones, as the ones that are most easily experimentally implementable. On the other hand, these algorithms here on the right, they might require some non-trivial experimental capabilities. For instance, this concept has been linked to quantum memory in the sense that imagine how you would try to implement a multi-copy algorithm in a scenario where you have an experiment that spits out a state row or like fresh copies of the state. Well, basically what you have to do is your experiment gives you some state row, but then in order to make space for another copy, you sort of have to take that state, transfer it to some quantum memory where you can keep it for some time, then run the experiment again to get a fresh copy, and only then you get to have two copies at the same time. So that's why some people also refer to the single versus multi-copy distinction as having quantum memory or not having quantum memory available to you. Okay, so while this is all nice, like it's still maybe not clear why theory people have looked at this so much. But the answer to this question is that from a theoretical side, we can actually often prove some quite big separations between the power of these algorithms. In particular, it turns out that often for scenarios or tasks that we care about, the single copy algorithms are much worse than the multi-copy ones. For instance, like a canonical example of that is the task of purity testing, where we would like to test if some unknown state is either pure or maximally mixed. So it's known that in the multi-copy setting, if we have this multi-copy power available to us or the experimental capabilities, then we can get away with just constant amount of copies. There's no dependence on the system size. And this algorithm is basically just running the swap test a couple of times. So you might know that the swap test, if you run it on like two copies of the same state, basically the success probability is directly related to the purity. So that's how that works. But in the single copy case, it has been shown that if you don't have even two copy capabilities and you're stuck with single copy, then you get an exponential amount of samples that is suddenly necessary to decide this question accurately. So a huge separation, really. And something similar is also true, for instance, for Pauli shadow tomography, where if you have multi-copy capabilities, you need linear amount of samples. But again, you need exponential amount of samples if you only have single copy power available. And this, as we will see, the same thing applies to the stabilizer case. This is sort of like foreshadowing our result already, but like, again, addressing the answer, the measurement that you proposed, Jello, is precisely one that, lives here in the multi-copy regime. And it's very good and very powerful, but yeah, so it might not be so easy to implement. Okay, and if you want to know more or are just getting familiar with these kinds of separations, then I think a perfect first reference to look at is this paper by Sitan Chen and co-authors, which is called Exponential Separations Between Learning with and Without Quantum Memory. Like, you can really understand how you can prove these kinds of bounds from that paper very nicely. Okay, so this brings me to our results. So what did we actually do? Hopefully we have digested the title of the talk or of the paper also by now. We're looking at stabilizer testing, where we wanted to decide if an unknown state is in that stabilizer set or some non-trivial distance away from it. But we're restricting our attention to only considering algorithms which have the single copy paradigm coming with them. So we're restricting ourselves to a smaller set of algorithms, but potentially algorithms that are much more feasible to implement. And maybe it's also worth mentioning that these algorithms, they might even have benefits that go beyond this. So for instance, like last year there was a paper by Omar Fazi and some co-authors that looked at some non-IID setting of quantum learning, and they showed some positive results for single copy algorithms, which they are not sure if they actually can also be extended to multi-copy algorithms. So there might be some benefits of single copy algorithms that apply even when we have fault tolerant or like very, very good hardware available to us. All right, so what do we show? Our first result is an upper bound. That means we show the following theorem. We show that there exists a single copy algorithm for stabilizer testing that uses a linear amount of copies and runs in efficient time, so n-qubit. Yeah, that's our first result. And our second result is a bound that complements this sample complexity from below, so a lower bound. And that theorem says that any single copy algorithm for stabilizer testing must use at least square root of n copies of the unknown state. So if you take these two together and only focus on sample complexity issues for now, then we show that the optimal sample complexity for single copy algorithms lies somewhere in between square root of n and order n copies. And now we can sort of compare this to previous work. And here's the multi-copy algorithm that I was talking about before. This is from a paper from David Gross, Sepanitsamy, and Michael Walter from 2017 is where it originally came out. And they, as I said before, they show that there's a system independent complexity in the multi-copy case. And we show that there is some, if you only have single copy access, your sample complexity will depend on n in some non-trivial way. And so there's again a separation. It's just that for us, the separation is much more fine-grained. It's only at most a linear blow up. And this sort of, I guess, has to do with like stabilizer states being just a much more structured set. So we wouldn't expect a big separation anyway, but there's some separation. Okay, so this is really the already summarizing our work. And yeah, I guess I would now again take questions before going into the details of the algorithm, maybe. If there are any.
Yeah, Marcel, I'm going to ask you an annoying question.
Sure.
Do you, with the gap, which of these, the upper bound or the lower bound, do you expect to be the one that is, limited by the proof technique rather than being the true bound?
Right. Yeah, Jonas and I, we both suspect that really O of n is the right answer, but we are working on improving our proof for the lower bound, but it really goes into the details of like understanding moments of the Clifford group even better than we are doing so far. So yeah, I'm not sure if we are going to be able to do that, but everyone that I've spoken to so far, including David Gross, were like leaning towards believing that the right complexity is O of n. Yeah. Alrighty. So yeah, now I had to make a choice. I guess the time is not sufficient for me to explain like in detail both the algorithm and the lower bound. So I decided to just walk you through the algorithm because it's fairly simple and hopefully somewhat instructive, and then give some comments on the lower bound, but not in so much detail. Okay, so let's get going. As I said, the algorithm is actually fairly simple, and so like I thought it was like a good idea to just walk you through it and like have you see it one time. So it proceeds as follows. The first step is that you sample a random global Clifford unitary. And this can be done efficiently on a classical computer. Like you just need n squared bits to describe a Clifford. It's not too difficult. And then if you have this Clifford unitary, classically, you can then go and quantumly apply it to your unknown state. So you just rotate your unknown state by this random Clifford unitary and then measure in the computational basis. Okay, and now you can actually, within the algorithm, this is actually not done only once, but it's done over and over again, like 2K times. So you take the same state, apply the same Clifford, and just measure over and over again until you have collected a lot of data. And this basically already summarizes the quantum part of the algorithm. It's very simple. So the rest of the algorithm is really classical post-processing. Now, hopefully it's also clear from this picture that this is a single copy algorithm. At no time are we applying any entangling measurements. We're only ever measuring one copy of the state at once. Okay, and now let's look at the classical post-processing. The first thing that you then do is you combine pairs of outcomes. This step is not so important. It's just a mathematical convenience because in the stabilizer states, there's some affine structure that's sometimes a bit annoying. And by adding outcomes from some affine subspace, modulo 2, you can actually go to a linear subspace. So you're basically removing some affine shift that is otherwise a bit tedious to analyze. But really, this step is not super important. But now you've ended up with y1 to yk, which are bit strings. And you can stack these bit strings, taking them as rows of a matrix. And then you compute the rank on this matrix. And once you've done that on your classical computer, you then make a simple case-by-case distinction, namely if the rank of this matrix came out to be full rank, then you output a 1. And if it's not full rank, you output a 0. Okay, now how does this lead to a test? Well, basically what I showed you now is one round of this algorithm. And now you just have to repeat this round a bunch of times, where now between the rounds, this Clifford will change. So you will resample a new Clifford, gain some new information. And you just need to do this constant number of times if your epsilon precision that you want to get to is constant, and average the outcomes. So you will average some zeros and ones, and this will give you some number that lies somewhere between 0 and 1. And then in the last step, now basically comes the magical part. You compare this number that you got out, this average, and you just check if it's smaller than 0.42 plus epsilon. Then you declare that your state was a stabilizer state. And if it's larger than this number, you declare that it's not a stabilizer state. Okay, so this is the algorithm, but now probably you're wondering, what is this magic number 0.42? Why is it there and why does this work? So why does this work? And let me just give you some idea of like what is going on. So the first thing is that if you just look at the algorithm again and basically blur out the details a bit, then you can understand that this algorithm, or at least one round of it, is really just a stochastic process that ends up outputting some random variable that takes values either 0 or 1, right? It's just there's some randomness here in the sampling of your global Clifford. Then there's some inherent randomness in the measurements. So there's randomness, and out comes some number that is either 0 or 1. Okay, and what are you doing when you're repeatedly performing this algorithm and averaging the outcomes? where you're just basically estimating the probability that this stochastic process gives out the number 1. Okay, so in the infinite sample limit, if we were to do this over and over again, this mu would tend exactly to the probability that the stochastic process ends with a 1. Okay, and now if you analyze the stochastic process and assume that the input state, your psi here, was some stabilizer state, then you can find that you can actually compute exactly analytically what probability, with what probability you should see the output 1. And that number is roughly 0.4, which is what we had on the slide before. And how can you see this? Well, first of all, if your input state psi here is a stabilizer state, and you're applying a random global Clifford to it, then you've basically already randomized over all stabilizer states. So that explains why the value is the same for all stabilizer states. And then, like, I don't really have the time to show you the details, but you need to know some things about, like some facts about symplectic vector spaces. In particular, you need to know numbers of how many Lagrangian subspaces are there, and how many of these Lagrangian subspaces satisfy particular additional condition. And then this ratio is basically exactly this number here. So as the upshot is really, for stabilizer states, we can exactly compute this number, and it is this value. Now, for non-stabilizer states, and this is what I would say is our key contribution, is that we can show that for any other state, the output probability of seeing 1 is larger. And so this explains why the test works. If you see an average here that is comparable with this, then you can declare stabilizer states. If you see something that is much bigger, then you know that you're in this case. Okay, are there any questions on this? I can also try to give more information, but maybe towards the end.
Yeah, I mean, I just wanted to have a quick question now. So for the non-stabilizer, so it's at least bigger than this number, wherever it comes from. But I suspect it's actually much larger.
This is a good question. So yeah, this touches on something that I was actually only going to mention in my open questions, but yes, you're right that, so this depends very much on the input state. So in general, like the way that I think about this is that if your state has more magic, this number is going to be bigger. So it's going to tend to 1. The more magical, the further away you are from the stabilizer states, the more this number is going to go to 1. But unfortunately, I believe that this relation is not, how to say, it's like I can't pin down the exact relation, which also means that this algorithm is probably not a tolerant tester, if that means anything to you. So for a tolerant tester, this is something that has recently been very hip in the stabilizer testing literature. And basically what you would like from a test is that if you're very close to a stabilizer state, you would still want to accept. You would still want to say, okay, this is not exactly a stabilizer state, but I can tell from my test that it's very close. And I believe that this test that we have developed actually cannot do this because this relation between magic and this number here not being very good, like not being very smooth somehow.
So Marcel, do you mean that even if you change your rank statement into a statement that talks about like rank with some perturbation, like close to inevitable distance, a matrix that has full rank, rather than talking about actual rank of the matrix to make it more robust, it still doesn't work? Is that what you're saying?
This is something that I have to discuss with some people, but right. So like what you would like to do is you would like to make this rank thing robust, but this rank is calculated over a finite field. And as far as I'm aware, there are no good ways to make this robust.
Mhm.
Like for if your matrix had like real entries, then yeah, they're like norms that capture sort of robust versions of like ranks. But I'm not aware of anything like this in finite field world. Which, yeah.
Okay, but the underlying distribution is continuous, even though the measurement outcomes are discrete, right? So maybe there's an avenue through there or something.
Yeah.
Can I also ask? So like, it bugged me a little bit your definition of stabilizedness or whatever at the start, but I see kind of now, because I guess like, you know, typically you'd want to measure distance from like, say, the stabilizer polytope or something like this. But obviously, you know, taking convex combinations even of stabilizer states, which have no magic in this setting, would give you a different rank. And then it'd be higher rank and you'd be, okay.
Yes, and as far as I'm aware, there are no, even if you allow multi-copy capabilities, there are no tests known that would test for these like better ways of defining magic, like including convex, like stabilizer hull kind of things. Yeah. Okay, cool. So the last thing that I want to do is quickly comment on the lower bound now, and just like give you a feel for what technical tools you need to show such a bound. Okay, so if you have ever entered the business of showing lower bounds, then you've probably come across like this need for finding a good instance that you can start proving your lower bound from. Usually the problem that you would like to prove a lower bound is not super nice, and you sort of want to find a sub-instance of the problem that is easier to grab on and then start from there. And the easier problem that we show our lower bound for is the following. It basically comes down to distinguishing a random stabilizer state, so random pure stabilizer states, from the maximally mixed state. And like, it's not difficult to show that if you have a stabilizer tester, then you can also solve this problem. So there's a reduction between these two problems, but this one is easier to solve, in particular because here the maximally mixed state is so nicely symmetric. Like it looks the same in every basis and so on and so forth. So this is the problem that we actually show the bound for. And then there are two ingredients really that go into it. The first one is the realization that single copy algorithms are generalized by positive partial transpose algorithms. And what I mean by this is that sort of in the same way that you can generalize sort of separable strategies and LOCC strategies and then PPT strategies in other contexts, the same can be done here. So a PPT algorithm for me is just one that where the corresponding POVM that your algorithm implements, the POVM elements have to satisfy a PPT condition. And these kinds of strategies are then more general than single copy strategies. And nicely, the PPT condition is actually something mathematical to grab onto, whereas the single copy condition, sort of. It's not so clear how to mathematically model it in a way that helps you even to get going. So by showing a bound against PPT algorithms, we're effectively immediately also showing a bound against single copy algorithms because the PPT ones are more general. This is the first ingredient. And the second ingredient is just knowing your Clifford moments very well. And this is basically also where I needed help, and then Jonas came in for the help, and he was already an expert on this before, and I spent a long time of last year understanding this. But if you understand this and know how to work with it, then you can combine these two things and actually prove something about positive partial transposes of moments of Clifford operators. Right, yeah, this is on the technical side, sort of what goes into proving a lower bound. And this already brings me to the end of the talk. So in summary, we studied stabilizer testing, which again is the task of distinguishing stabilizer states from non-stabilizer states. And we looked at this in the single copy setting. And our main result is the sample complexity characterization. And okay, basically we already touched on both of the most pressing open questions that arise from this work. So there's a gap in our characterization still. It's small, but it's there. And it's somewhat unsatisfactory for me that these two bounds don't agree yet. So it would be nice to close this, but unfortunately, I think from discussions with like some other experts, for instance, David Gross, it seems like this might require understanding Clifford moments even better than what is currently possible or currently in the literature. So I'm not entirely sure if this will work out in the near future. And the other thing is that really what you would like is, or really what I would like to see is an algorithm that goes beyond testing for zero magic. So a stabilizer test, basically, if you run it and you see a reject, if you see your state is not a stabilizer state, you still have no idea about whether the state has a lot of magic or maybe just a little bit. What you would really like is some way of estimating the amount of magic. So really quantifying, not only deciding if it's zero or not. And because of this problem that I talked about earlier, about this number not really corresponding nicely to the amount of magic, our algorithm is currently not capable of producing such an estimate. And yes, I wanted to mention that there is a sample efficient way already for estimating magic in a single copy manner, which is just running classical shadows on your state and estimating the fidelities with all stabilizer states. This works out from a sample complexity point of view, but is, of course, super inefficient computationally. And yes, so I would like to improve this if possible. All right, so this is the end of my talk. I'm happy to take some more questions if there are any.
Okay, thank you very much for very wonderful and informative talk. Yes, yeah, so we have like a bit of time. Yeah, we have quite some time for questions from the audience. So if you have questions, feel free to just unmute yourself and ask them now.
Yeah, thank you for the very nice talk and work. So I'm wondering about the gap you mentioned. As Hecab already asked, you suspect the right scaling will be the linear in n, but I checked your paper earlier. It was a well-written paper, and you mentioned that you suspect there is a sublinear scaling that's possible. So what's the good scaling? You was suspect linear or sublinear for this algorithm?
Yeah, so I like after like we put this on the archive, I had a lot of more discussions, and I think both Jonas and I now tend to suspect that the linear one is the right one. Something that I didn't mention in the talk is that there's actually a different proof strategy in the literature for proving bounds against single copy strategies, which is in which is presented in this paper. And actually, if you know this field, then like you know that Sitan Chen and his group in particular, they are the masters of proving these bounds. They have sort of endlessly developed the techniques, and we tried originally before I even reached out to Jonas. I tried proving a bound in our case from the techniques in this paper, and it was not possible. Like there was something in the stabilizer state, which we also explain in a bit of detail in some like section of our paper, that just broke this. And because we had found this, that this proof strategy just wouldn't apply in our setting, or we didn't know how to apply it to our setting. Like we were like, and still are a bit doubtful if maybe this gap that we were talking about might still lean the other way. Yes, but I think, yeah, I personally, because also of the lack of imagination of coming up with a better algorithm, I am stubborn, and I want to think that the algorithm that we have given is basically optimal. So, yes.
Yeah, I see. Thank you. Another question is probably about the magic part. I'm wondering why you think the classical shadow can help in improving the magic part, because because there is no structure of the magic part. So do you need to like, for example, like writing the magic in the state and see how far it is from the stabilizer state, or somehow try to approximate them? Is that the approach
Maybe,
you think?
yeah. Yeah, thanks for the question. I think probably I didn't explain this very well. So classical shadows are this like very weird thing where like their sample complexity, or the sample complexity of like doing classical shadows with global Cliffords, is very low for what you can achieve with it. For instance, if you want to estimate fidelities with some unknowns, like of some unknown state that you're probing with some target states, then you can get exponentially many fidelities just using a linear amount of samples. The problem with classical shadows is that this almost never helps you in any setting, because to compute these fidelities then takes exponential amount of time. And so we're in this weird situation where basically I know that the sample complexity of coming up with a single copy algorithm for estimating magic, that is low, because classical shadows solves that problem efficiently if I just care about sample complexity. But this doesn't answer my question really, because the classical shadows apply to the setting They don't give rise to a time-efficient algorithm. And actually, I have come across this phenomenon in various other settings before, where you can easily see that classical shadows solves one of your problems sample efficiently, but then you have no way of making it time efficient. And I think there was even a recent paper where I think in one of these agnostic learning papers, I don't know if you're familiar with this, but there was, I think I saw in QAP, there was one of these things called learning the closest product state. They really put the nail in this problem where they showcase a problem where classical shadows, you can solve it sample efficiently, but they can prove a time complexity lower bound that is super polynomial. So you can basically see that thinking about classical shadows as a method for solving something is really not the right way to go, because you're never going to make it time efficient.
Yeah, I see. Thank you.
Thank you for the question.
Yeah, I think I just wanted to add that because we recently also had like someone who gave a talk on like efficient sort of like I think it was like efficient shadow tomography. So I think like the claim that you're making is really if you're doing things single copy, but if you go to multiple copies, then it's actually sort of possible to get also at least some improvement in the, I think, time complexity. Yeah.
Oh, yes.
Yeah, I think like,
yes,
for example, in their case, they were doing, if you allow 2 copy measurements, there's already certain improvements you can make for certain observables. Yeah.
Totally, yeah. And like actually most of the 2 copy things, in most cases, 2 copy things are perfectly fine. For instance, for Pauli operators, you just need 2 copy capabilities.
Yeah. All right. Okay, so is there anyone else with questions? Yeah, I think we officially still have like 5 minutes.
Maybe can I ask, what is like your group working on roughly? I mean, I know what Jakob has worked on in the past, but maybe the rest of you.
I think like in some sense, like everyone is sort of working on their own projects. So like for me, I'm basically my background is like in non-locality, but Mincho is actually asking me to do some work in crypto, which actually brings me to the question that I wanted to sort of ask. Okay, if no one else is asking. So because I have no intuition of like why this computational difference testing works, right? But it kind of reminds me, so one of the things I've been looking recently, if you're probably familiar, or hopefully you're familiar with like pseudo-random unitaries. So there's like a construction like called the PFC ensemble, where you multiply a permutation, a binary function, and a Clifford. So in that case, like the role of the Clifford there is sort of like actually you're doing some Clifford twirl, and it uses some lemma where if you have some state and you take an average over the Clifford twirls, which is sort of like what you're doing because like a C tensor things on T copies, then you go to the distinct subspace, right? So if you look at the basis of T copy Hilbert space, like, and you only consider those strings where you have unique strings, this is what I call the distinct subspace. And the probability that you go into the distinct subspace is high. So this is the thing that gives me the intuition that, oh, that's why your rank is going to be like full rank, because the tendency is like if you do this kind of measurements, then at least that's where my intuition comes from. Of course, it's not the full intuition because it doesn't distinguish between states. The result that they have is actually sort of like for any state, and you do a Clifford twirl, then the probability that you go into the distinct subspace is very high. Yeah, but I guess, yeah, I don't know. I wanted to sort of like, if you have some intuition, like, can you give me some intuition of why this difference? So somehow, instead of just looking directly, so in my case, I was just looking directly at the excess, what you were calling the excess, and sort of like forming the matrix of that. And if I do that, then it will always be full rank, or at least with high probability, it will be full rank regardless of the state that you're measuring. But in your case, somehow by sort of pairing things together, then now you can distinguish between a stabilizer state and something that's sort of sufficiently far away.
Right. Okay. Let me. So I prepared one slide. I have this formula here, which I prepared in case someone was going to ask about the pairing. Okay, and this now already goes in like knowing things about stabilizer state that not like that go beyond the definition. So one thing that is known about stabilizer states is that they can always be written in this form up to some global phase. Okay, what is this form? This is the expansion in the computational basis. And you see here that you only get bit strings that belong to some affine subspace of basically all bit strings. Okay, so if you measure a stabilizer state, like if it is of this form and you measure it in the computational basis, you can basically forget about all these phases here. You only see a bit string that is uniformly randomly sampled from this affine subspace. Okay. And now, as I said before, this is a bit annoying because we don't really want to work with affine subspaces. We would like to work with linear subspaces. So what you can do is you can just sample twice, then add the two, and you'll get rid of the whatever affine shift is there. However, I'm not sure how this relates to your intuition. For me, this is just a convenience because it makes the analysis much cleaner. Because I can now like just think about linear subspaces. I don't have to worry about affine shifts anymore. But it's really not, I wouldn't even say that it is necessary in our algorithm. It just makes everything much easier to analyze. But I'm not sure I understand the definition of what you call the distinct subspace. So it's bit strings, but they have.
Oh no, like if you have like T copies, so like for each copy you have like a Hilbert space, right? So if I have a computational subspace there, so for the first copy I have like x1, like the basis states there, and then x2, and you only consider sort of like tensor products of strings that are distinct. Then that will sort of like if you take the projector onto those, that will give me the distinct subspace.
Interesting. And yeah, okay.
Yeah. But yeah, I mean, I guess like I also like, I mean, maybe I should be careful about making the claim that I'm making since I haven't really gone through how they're proving the result in that case. But I sort of like, yeah, it just reminded me of that. Of course, it could be totally unrelated, but
it sounds
yeah.
Similar. Yeah.
Yeah.
I will have a look. I will have a look. Maybe I can also learn something from that.
But definitely, like what I was thinking doesn't help you distinguish. So it's sort of a result where, like, it just says that the probability that you go outside that distinct subspace for any state is sort of like very low. Like.
Jakob, you were going to say.
Oh, sorry. I was just going to say I've got to run to another meeting, but thanks for a very nice talk.
Oh.
See you guys.
Yeah.